Here we're going to talk about lines of position and fixes. So a line of position is just any line or arc that you plot down on a chart where you know for a fact your ship is somewhere along it. You can't actually prove exactly at what point along the line you are, but you know you are on that line somewhere to a reasonable degree of error. A fix, however, is when you can identify the exact point where your ship actually is. Once again, with a reasonable margin of error. Officially, you should only be satisfied with a fix if you're basing it off of 3 lines of position. That's if we're talking visual or radar fixes. Any 2 lines that intersect will obviously give you a single point of intersection, but you shouldn't trust that as a fix because there's no redundancy. You haven't proved that that's where you actually are. So you need 3 coming together at the exact same point to actually be satisfied that that is a true fix. So a line of position could be one of 2 things, realistically. It could be, if we're talking entirely in terms of terrestrial navigation, it could be a bearing or a range. A bearing just being the sight, the sight measured off of a compass you have towards looking at a specific object. That could either be visually or on radar, though radar bearings aren't particularly accurate. And then a range is the distance away from it, and you can pretty much only get that off of radar or theoretically LORAN if it were still operating. So between bearings or ranges, you could use any combination of them to get yourself a fix. So here's one example. Let's say we're going to work with Montauk Point again. Let's say you take a visual bearing of Montauk Point Light at night, and you see that it bears, let's say, 230 degrees true. Okay, so now you want to actually plot that on the chart. You know that it bears from you 230, but you want to actually see where that places you in reality. So you take your triangle, you bring it to a meridian, place your pencil, and then you adjust the triangle so that 230 lands, you can see, right at the edge of the meridian. And you slide the triangle up, maintaining that angle until the edge of the triangle is hitting Montauk Point Light and the angle is still accurate. Once you've managed to do that, you can then draw a line off of Montauk Point Light going northeast, because if it bears 230, this could be either 230 this way or 050 this way. Now, if it bears 230 to you, that means you're looking down at it. So you would be going actually in the opposite direction to draw the line, and then imagining yourself somewhere over here looking down at it. So now you can see there's our line coming from the light upwards here. This is a line of position, an LOP, but it's just one. So you can say with a decent degree of confidence that the ship is somewhere here at the time of the shot, but you don't know where. It could be anywhere along this line. It's all equally likely. But let's say you then take another shot. If you see right here, you can see this says Shagwong Point. It looks like it's a point of land. It looks like it has relatively steep edges on either side of it, though it kind of turns into a beach right near the tip, but you should still be able to potentially get a decent visual shot off of that beach right there. And so then you could take what's called a tangent bearing, where you just aim at the furthest point of land that you can see visually and get that bearing off of that. You could then correlate that to the furthest point of land that should be visible to you. So let's say that bore 0.87, for instance. Now you measure out 0.87. Let me get that visible. Okay, you can see there's 0.85, so 0.87 would be just that, nearly due west of you. Oh wait, I'm sorry, this would be 267. It bears 267 because it's west of you. So nearly due west of you at 0.87 or 267. And then you plot out that line and you can see it intersects your first line of position right there. Both of these are LOPs. You know you're somewhere along here, you know you're somewhere along here. Meaning realistically you are probably right here, but you can't prove that because any two lines will intersect somewhere unless they're parallel. So you need a third LOP to be satisfied with that shot, to actually be satisfied that you know where your position is. So we got to find one. Now, I can't just make up in my head what bearing or range would be accurate here, but just real quick. Okay, let's say the third thing you did was then you took a radar range off of, I'll zoom you in, yeah, off of that beacon just south of Montauk Point Light that you can see is labeled a radar beacon, R beacon. What that means is that you can very easily detect this off of radar. It's obvious, it's not going to get blocked by anything. You can get its distance relatively easily. And let's say you measured that distance off of radar and got 2 nautical miles, just thereabout, almost 2.1 nautical miles. So if you then went to your range scale and measured out just about 2 nautical miles right here, and then brought that back over and centered one of your ends at the beacon, and then drew an arc in the general area that you're looking for, you can see that that arc right here intersects your first line of position and your second line of position almost perfectly. So your bearing to Montauk Point Light, your tangent bearing to Shagwong Point, and your radar range off of the Montauk Point radar beacon all indicated that you should be right here. So this is now actually a true fix. This is your position. Fixes are labeled multiple in a variety of ways. In this case, it would be a circle because it is a visual bearing. So a bearing made off of a fix made off of visual bearings is labeled with a circle. A fix made off of radar ranges is labeled with a triangle. Technically, if you were to combine the two, like I did here, with a bearing and a range, you should treat that as a composite bearing and do a circle and a triangle. Though that's not always required. It depends both, I suppose, on the teacher you have and then in the future on the captain you have. But technically, this is a composite fix, so triangle and circle combined. If you were to have just 3 bearings, it would be a circle, and just 3 ranges would be a triangle. GPS fixes are based off of squares, and then anything with celestial is considered a visual fix as well. So you got your fix right here, and you labeled it properly. The other thing you got to do is you've got to label the time of your position of your fix. So let's just say 0800. You took this shot at 0800, and so you write that at the bottom horizontally because that means it's true, right underneath or to the side of the fix, wherever you best be seen. Let's try another one up here. So let's just do 3 bearings here. So let's say you're over here near Fisher's Island, and you take 3 bearings off of these various lights. Remember, you never want to take a bearing off of a buoy because they're not stationary, bearing or range. You don't want to get any information off of them. They're just for navigating by eye. So let's say your first bearing to Watch Hill Point is 060, and you have to measure an angle of 060. And then once that's ready, you got to take your second triangle, move it up until it reaches Watch Hill Point, and then plot that out. And you get this first LOP right here. Let's say this breakwater light bears due south. So now the nice thing about when something's due south or due north or due east or due west is you don't have to measure your exact angle. You can just take either a meridian or a parallel and draw a line that's perfectly perpendicular to them using the triangle. So in this case, if something's due south of you, you can just line up your triangle to be perpendicular with a parallel, because a parallel goes due east-west, so then the line you get would be due north-south. And then you could draw a line straight off of it. Whenever you get something like that, it's just nice and convenient. It makes your life a little bit easier. So then you've got a second line of position right here. And then your third line of position, I gotta actually measure this because again, I didn't make up any of these bearings or ranges to begin with. Measure it out. 3, 2, 1. Okay. You take the bearing of this light and it bears 3, 2, 1 true. So then you come back here and again, you measure an angle of 3, 2, 1. Like that. And you move that over to here. And you get all 3 lines intersecting right there. So you draw just a circle because this is an entirely visual fix. You just got it off of bearings. And you label that with the time. I'm just going to say 0700 for this one. Now, as a brief aside, you need to know what light you're looking at. Here I just said, oh, you get a bearing off of Watch Hill Point, you get a bearing off of this breakwater light, you get a bearing off of this one. But how do you actually know what light you're looking at? Well, you have to look at their characteristics. So we haven't had the video on how to read light characteristics yet, but every light has its characteristics labeled. You could see like this one says OC, W, and flashing red, or AL, OC, W, and flash FL red to 15S. Means alternating between occulting, I've never actually seen this before that it's alternating like that, occulting white and flashing red every 2 seconds for 15 seconds. So this could mean this is honestly a particularly odd one, that it alternates between having an occulting white light where it's on more than it's off white, and then flashing red twice every 15 seconds. It has that full period of light characteristics. Whereas this one here is flashing red every 4 seconds, and this one is flashing every 6 seconds. When it doesn't have a listed color, you can assume that that's white. So when you're on your ship looking for these lights, you'll know their characteristics in advance because you've looked on the chart and you're kind of aiming for them. And you can, once you spot something that matches these descriptions, then you know you're actually looking at Watch Hill Point light, or you're actually looking at this breakwater light that doesn't actually have a name, or this one that also doesn't have a name. And you could use that to then place your fix. Let's do one more fix entirely off of ranges. So we're going to come over here This is the race, by the way, the entrance into the Long Island Sound. Let's say here's Race Point Light right here. I only use lights. I'm using lights so much for the ranges here just because they're very conspicuous objects. This one's 67 feet, so you can get it on radar very easily. Whereas you see this point of land at the point of Fisher's Island, doesn't have much of an explanation, but this could very easily be a soft beach that wouldn't necessarily give a good fix on radar. But let's say using Race Point Light here, you find that you off of radar that you're a mile away from it. You're a mile away from a radar object that, based on the context of your surroundings, you can tell is Race Point Light. So you make an arc that is 1 mile. That is 1 mile around Race Point Light. Now you could technically you should mark it as a full circle, but if you know that it's bearing east of you, you can just make like a semicircle. It doesn't need to be perfect because you already know generally where you are. Let's say Little Gull Island Light bears or has a range of just about 2.7 miles. So then off of radar. So then you come here and you measure, here's 1 mile, 2 miles. So then you have to come and get 2.7. So then you place your divider tip or your compass tip at 2 points at Little Gull Island, and you draw another arc that passes through your first arc right there. I'll zoom in so you can see better. So you can see here's my first arc from Race Point Light, and here's my second from Little Gull Island Light. Now they intersect at 2 different locations because they're both arcs. So you don't know yet whether you are here or here. You have to get a third range before you can actually have a definitive conclusion about anything. So there we go. Now you get another bearing off of, or another radar range off of this light here, which also doesn't appear to have a name, but it's Bartlett Reef light because it's the light coming off of Bartlett Reef. A lot of times you can just assume their name off of context like that, and I just off of memory, having done this before, I can tell you that this is Bartlett Reef Light, sorry. And it has a range of, actually I forgot. It has a range of 3.7 miles. So then you come to your latitude scale, because you can use that for distances as well. Measure out 3.7 miles. You can see 1, 2, 3, 3.5, 6, there's 7 right there. So you come to Bartlett Reef, zoom out a bit. There we go. And then it intersects. You draw your arc, and you can see all 3 of them, 3 arcs pass through each other right there. So you draw a triangle because this is an entirely radar fix, and you label the time 1000 for this one. So that's how you would be able to measure either an entirely visual fix off of 3 visual lines of position, an entirely radar fix off of 3 radar line arcs of position, and a composite fix off of multiple visual bearings and a radar arc of position. You'll oftentimes use a lot of composite fixes because, especially if you're using something like a lighthouse, you can easily get its range and its bearing at the same time, seeing as it's so easy to detect on radar. So these are probably more common than the others. but you should just remember the basics of what an LOP is, that it could be a line or an arc, and that you need at least 3 before you can determine something is a fix. More is obviously always welcome.